All right, so finding area with parametrics. Let's remind ourselves how we found area with normal functions. I guess if we had a function like this and we wanted to find the area from a to b, we would, what would we do? Well, we integrate from a to b and we'd multiply by y dx. Because each of those is y times dx is, well, y is the height of a little, if you think about a little rectangle here, y was the height and dx was the width. And we're just summing those up over the interval. So with parametric, you can just make the substitutions, just like we did so many times. With u substitutions, we can make parametric substitutions. So we'll have x as it will be a function of t, and y will be a function of t, and so if you have x equals x of t, then dx dt is equal to x prime of t, and so that therefore dx is equal to x prime of t times dt, and y is equal to y of t. So what you could do is you could integrate then from, well, wherever this is, t equals t sub 1 to t equals t sub 2. Let's say that it's at t sub 1's at a and t sub 2's at b. You can integrate from t sub 1 to t sub 2 of y of t times x prime of t dt. And that's because what we have here is this is the y and this is the dx. All right, now let's look at an example that's kind of an interesting example. All right, I want to look at this parametric. X equals t squared and y equals t plus 4. So if we eliminate the parameter, we can solve for t in the second equation, the y equation. Say t is equal to y minus 4, and then sub that in. So x equals y minus 4 squared, or y is equal to plus or minus root x plus 4. So just the equation as a x in terms of y, or y in terms of x. And its graph, hold on a second, its graph is going to look like this. All right, so here it is. It's a sideways parabola that's just shifted up 4. And so first thing I want to do is to think about the area underneath, because this is square root of x plus 4, and this is the negative square root of x plus 4. And first I want to consider just the area underneath the top curve, the square root of x plus 4. From x equals 0 to x equals 9. So, all right, so there's the integral. And again, we're finding this area inside this region right here. And it's going to be 54, which shouldn't be too surprising. Now let's look at the parametric integral. And one thing to look at is at this point right here, at this point right here, t equals 0. And at this point right here, t equals 3. So here is the parametric integral that will do the trick. So we integrate from t equals 0 to t equals 3, and we've got y times, and this is dx. Because dx dt will be 2t, dx dt will be 2t, and therefore dx equals 2t dt. So we're just doing y times dx, and we're integrating from 0 to 3. And if you do this integral, you can check the math, but this comes out to 54. So you're probably wondering, why is this interesting, Mr. Ellison? Well, this one is not interesting, this part so far. But now I want to consider the area inside the parabola. If I only wanted to find the area inside the parabola, rather than just the area below the top half, from x equals 0 to x equals 3. Let's look at the area inside the parabola. Okay, so to find the area inside this parabola from x equals 0 to x equals 9, to the area inside here, we traditionally would have had two different ways of figuring it out. One was to integrate with respect to x and think of the two halves, the top half and the bottom half, and integrate from 0 to 9 and do the upper y value minus the bottom y value, which would give us the height of each little slice there, and then multiply that by dx, and then integrate that from 0 to 9, and you get 36. Likewise, we can integrate with respect to y, and y goes from 1 here up to 7 there, and we could think of our rectangles the other direction, in which case the height will be this y value, which is 9 minus, this x value 9 minus this x value, which is y minus 4 squared, and then times the height of the rectangle, which is a dy, and then integrate that from 1 to 7, and lo and behold, we also get 36. No big surprise. However, recall that before, when we did the area underneath the top curve, when we did the area inside this region here, we got 54. The area inside the red area was 54. And we got that a couple different ways, but one way we got it was parametrically. We integrated from t equals 0 to t equals 3. So t equals 0 was right here, and t equals 3 was right here. And what this is parametrically is this entire curve is actually from t equals -3. So t equals -3, it's here, and then it goes on this journey, t equals -3 to t equals 0, and to t equals 3. So begs the question of what happens if you integrate from t equals -3 to t equals 0. So what's going on with this area right here? Well, one thing I could do is I could think about the integral from 0 to 9 of negative square root of x plus 4 times dx. And if I do that out, I'll get 18. And so, yeah, this kind of makes sense that I get 18 because the area under the top curve was 54. That area inside this blue region was 54. And then I could subtract this 18, which is the area inside the red region, and then I get my 36 as the area inside the parabola. And all is good. Well, this is the parametric equivalent here, because we got t equals -3 right here, and we've got t equals 0 here. Well, is it the parametric equivalent? I don't know if that's the right word, but I'm going from t equals -3 to t equals 0, and I've got y, and I've got my dx. And if I do this out, well, let's see, I've got 2t squared plus 8t dt from -3 to 0, pardon the handwriting, equals, and then I'll have 2/3 t cubed plus 4t squared, evaluated from -3 to 0. I plug in 0 and I get 0. I subtract, and then I plug in -3. I'm going to get negative 18. And then if I plug in -3 to the next part, I'll get plus 36, which when I simplify comes out to negative 18. Negative 18. So this integral here is equal to negative 18. But wait a minute. I thought it was 18. Well, so what's going on here? Well, that means this, that if I integrate from -3 to 0, I get negative 18. And if I integrate, keep going and integrate from 0 to 3, that's 54. Negative 18 plus 54, well, there's my 36. So, darn it. So if I integrate from -3 to 3 of t plus 4 times 2t dt. That comes out to my proper answer of 36. But what gives? Why is this working? Well, why is this negative 18? Well, it has to do with the way I'm moving. Because when I'm going from t equals negative 3, and this is a subtle thing, but when I'm going from t equals negative 3 to t equals 0, I am moving to the left, which means my dx is negative. So what I have here is this part here is negative and this y is positive. So that is why I'm getting a negative answer here. Because on that stretch, because t is negative, dt, time is moving forward. But since t is negative, 2t is negative, and 2t dt is negative. And what does all this? Well, this is dx. dx is negative on that stretch. Y was positive on that stretch. But so this product here was a negative product on that stretch. So as a result, I was summing up a negative area on this stretch, negative 18, and then from t equals 0 to t equals 3, well, that was 54. So negative 18 plus 54 left me with 36 as the net area. So it's kind of bizarre when you're moving back and forth with these parametrics and you're finding area. It's something that is unexpected, but once you see what's going on, it hopefully makes some sense of why you had a negative, quote, area when you're integrating along a positive stretch of time.